Greetings, everyone. Welcome back into the wonderful world of Calculus 2. Time to take a little sidestep and talk about a third test in this course. I'd like to work some practice problems that I've given on an actual Calculus 2 test. And then you can finish up with a few other topics after this one and then be done with Calculus 2. The Calculus 2 topics for this test are covering conic sections, so all of your circles, ellipses, parabolas, hyperbolas, but in all of their standard forms and being able to identify all of the details like vertices and foci and directrices and all of those things that go along with understanding and graphing of a conic section. Parametric equations and polar coordinates. I know those don't exactly go together all the time, but they are two alternate versions of graphing and understanding functions. So they sort of go together in one category and they have the same types of applications. You need to be able to convert between the different forms of rectangular parametric equation and a polar coordinate of points and equations. You need to be able to graph or understand what the graph is going to be on one of these guys. And then you have to be able to perform any of the calculus demands that come upon a function, whether it's in rectangular, parametric, or polar form. Calculus being you need to be able to do derivatives and integrals of any of these three formats, rectangular, parametric, or polar. Okay, then we have a unit on vectors. And in this case, we're building up for multivariable calculus. So you need to be able to do vectors in either 2 dimensions or 3 dimensions. Being able to create them, from sight or from description, whatever. You need to be able to do all of the arithmetic of combining and resolving vectors. You need to be able to find angles of a single or between 2 vectors. The dot and cross products you need to be able to perform and also apply them to certain attributes of the vectors. And then, of course, there's applications with vectors like force and acceleration and work and all of the other applications that we've used throughout this section of vectors. Okay. As usual, I give the same warning that I always like to give, and that is, don't focus too much on the individual problems here. These are meant to be examples. Please try to get the skills that are needed to problem solve these types of setups. Okay? In these examples, see if you can either pause or beat me to the punch and use these to make sure that you've gotten all of those minor details out. But do not by any means memorize these problems. These are not supposed to be the entire universe of these topics. Okay? First problem is a parametric equation. So I have parametric equation labeled F, where x is t squared minus 4 and y is t squared minus 2t. And I even gave the graph when I gave this problem too. It is a sideways canted parabola that's been shifted over a bit. You can tell the vertex is beneath the axis somewhere over right here. Okay, so the questions that are posed are, I want you to find the line that's tangent to F when t equals -1. And I want you to give the direction of the concavity at that same point. Okay, and I know obviously you can tell where which way the concavity is going to be. If it's on the lower side, it's going to be concave up. If it's on the upper side, it's going to be concave down. The point is to use calculus to do it. Okay, and then also compute the area between the x-intercepts but under the x-axis. So computing the area down under here. Okay, so let's begin. To find the line that's tangent to F, we need some derivative action. Okay, so I'm going to start by writing down dx dt and dy dt. right? dx dt is equal to 2t. So you can do the derivative of each piece. Derivative of 4 is 0. And dy dt is going to be 2t minus 2. So therefore, dy dx is going to be dy dt divided by dx dt. 2t minus 2 over 2t, which I can reduce this to 1 minus 1 over t. And then the second derivative, d squared y over dx squared. Don't forget that the way that this works is I have to take a t derivative of this derivative, so 1 minus 1 over t, and then I have to divide by dx dt again. Okay, so the derivative of this right here is going to be 1 over t squared, right? Because you're just going to drop a negative 1 times negative 1. Derivative of the 1 here is 0. So I just get the 1 over t squared, and dx dt is still 2t. Okay, so then I'm going to get 1 over 2t cubed as the second derivative of y with respect to x, right? Because this is just going to be 1 over t squared times 1 over 2t, basically, is what I'm doing here, right? Because I'm dividing by the reciprocal of that. Okay, so I've got my my two derivatives here, right? That was the goal for the first guy over here. So finding the line that's tangent to f when t equals -1 then just requires a slope, right? So my slope m is going to be the value of the derivative, but at t equals -1. So I'm going to have 1 minus 1 over -1, because I'm just plugging in my t value there. Alrighty. So that's just 2. Next, I need an x value and a y value, right? So that I can set up my point slope form. I'll just say x sub p for point, right? So the x value and the y value here are going to be when t equals -1. So that gives me -1 squared minus 4. So 1 minus 4, of course, is -3. And -1 squared minus 2 times -1. So I have 1 plus 2, which is +3. Okay, so on the graph right here, you can tell it's going to be -3, 3, which is going to be this point right here. We're talking about that point right there. So then let's create the tangent line now. I'm going to use point slope, so that's y minus 3 is equal to 2 times x minus -3, which is going to finally give me y is equal to 2x. And then this is going to be 6 plus 3, so plus 9. So this is the equation of the line that is tangent. And that should sort of make sense to you, because if you look, the tangent line here is going to be the line that goes this way, right? It goes like this. So you can tell it's going to hit like right at 9 right there. See, that's our tangent line there. Okay, what about the concavity? So the concavity is going to be based off of our second derivative here, right? So d squared y dx squared measured when t is -1 is 1 over 2 times -1 cubed, which is just going to give me -1/2. And the fact that this thing is negative, right, is telling me that it's concave down. And that makes sense. Look, we're on this portion of the parabola right here. It should be concave down ever so slightly. I mean, the 1/2 is a small value, so it's not, concave down a lot, but it is concave down. It's curved in that direction. Next, compute the area between the x-intercepts and under the x-axis. So we're looking at the area underneath here, right? We're going to be adding up values here. And I drew the lines in that direction on purpose because notice it's going to be easier to do the integral by letting x count from point to point. Y is going to be the heights of our rectangles, and I'll just use dx as the thickness of the rectangles there. Okay, so in other words, I'm going to be integrating from x equals -4 to x equals 0, because that's where our two intercepts are. You can see -4 and 0. And if you're not sure about that, you can always let y equal to 0 and solve for the two t points, right? In fact, we're going to have to do that anyway. And then you can see where the two x values are. Okay? Or you can just ask, which t values cause the x to equal into the y equals 0. Either way. Anyway, so we're going from x equals -4 to x equals 0. Y is the height times dx is the thickness of our rectangles there. So then I just need to convert all of this into an integral that can be done just with my parametric form here. The y and the dx are straightforward. You can see right here that dx is going to be 2t dt. That's my dx right there. And then y is t squared minus 2t. So the integral portion, right, is pretty straightforward. Now we just need to set up the boundaries. I need to know what t values are happening when x is 0 and when x is -4. Okay? Also, you could check this with the y value equaling 0. So whichever way you want to do it. Okay, I'll just separate this out for a second. When x is 0, I have 0 equals t squared minus 4. Of course, this is giving me two different t values, right? This is going to give me t is either plus or minus 2. So there's a little bit of ambiguity there. But notice there are 2 points, right? It's down here and it's up here, right? So we need to know which one is which. Also, what happens when x is -4? So then I have -4 is equal to t squared minus 4. So I'm going to get that t is equal to 0 there, because t squared is 0. So that one's pretty definitive, right? T is equal to 0 right here. So t is equal to 0 at this point right here. And I know t is equal to -1 here. So just with those 2 points right there, you can get the flow of the parametric equation, right? It should flow in this direction. It's going to go around like this. So that's enough right there to determine that I know that I want the +2. Obviously, this point right here must be when t is +2, because it's flowing, counting in that direction. But if you're still not sure, you could always do, hey, where is y equal to 0, right? So that would be 0 is equal to t squared minus 2t. You can factor out a t and determine that this happens when t is 0 or t is 2, right? Well, we already knew t equals 0 was one of them, and then obviously t equals 2 must be the other one. So over here, the t equals negative 2 must be the y-intercept at y equals 8 right there. Okay, so that's enough information there to finish this out. I know that this is going to be t equals 0 to t equals 2. Luckily for us, we're flowing in that direction already, right? The parametric equation is going in the same direction that I want to integrate. Since this is an area though, and I can tell that they're all the same, right? There's no contamination of positive y values with negative y values. I don't have to split my integral, and I don't have to worry about anything. If I did come up with a negative answer, I can just do the absolute value. Okay, so let's finish this up. I've got the integral from 0 to 2 of 2t cubed minus 4t squared dt. So then I will integrate. I'll have 2/4, so 1/2 t to the 4th minus 4/3 t cubed from 0 to 2. Lucky for us, when I plug in 0, I get 0, so I'm not going to worry about that one. And then this is going to be equal to 1/2. 2 to the 4th power is 16. And then 4/3, 2 to the 3rd is 8. Okay. So let's see. I'm going to have 8 here also. 8 minus 4/3 times 8. And I did that on purpose because I noticed they were both 8s. I'm going to make this easier on myself and factor out an 8. And that's just going to be 1 minus 4/3 right there. Okay, so obviously 1 is 3/3 minus 4/3. I have 8 times negative 1/3. And I'm getting negative 8/3. Now, why is this coming out negative? Remember, it should. We're adding up negative y values. Okay, so when it said compute the area, right, we're just going to do the absolute value. Of 8/3. Next question. Given this parametric equation, locate any vertical and horizontal tangents, convert it into rectangular form, and use that equation to identify the shape, and then find all the important pieces of information. The names kind of give it away, right? Center, vertices, foci. It's going to be a conic section. And then graph it. Okay? So we have x equals negative 4 minus 2 sine 3t, and y equals 1 minus 5 cosine 3t. If you're familiar with the parametric equations here, then you know combining a sine and a cosine with the same argument is likely to give you some sort of circle or ellipse shape. Okay, that's a good thing to know beforehand. So locating vertical and horizontal tangents, I am expecting some if it is one of those types of shapes. So let's dig into that. To do the vertical tangents, then I need to set the derivative dx dt equal to 0. So dx dt here is going to be negative 6 cosine 3t. I'm just taking the derivative of this right here, right? The chain rule of 3 times the negative 2, of course, the derivative of 4 is 0. And then I want to set this equal to 0. So in other words, I'm going to be solving really just the cosine 3t. is equal to 0. Now, cosine is 0 at pi over 2 and 3 pi over 2. And then this this thing right here, the 3t, usually means that you have more cycles per thing. But for our situation, with the 3 in the 3t there is, it means that it's just going to draw the shape faster. Okay, so I have either 3t is equal to pi over 2, or 3t is equal to 3 pi over 2. That's where cosine is 0. So dividing by 3 here, I get that t is either pi over 6 or pi over 2. So then if I plug these values back in, right, notice that I've already got a cosine 3t in there, and both of these are going to obviously be when that's equal to 0. Okay, so let's get some coordinates for these two things right here. Right, if I plug in t equals pi over 6, then the coordinates of that I know is going to let the y be 1 minus 0 for both of them. Okay, because both of these, as we just purposefully designed this to where cosine is equal to 0. So this is going to be 0. So I know the y coordinate on both of these is going to be 1. Okay, so then when t equals pi over 6 here, I'm doing the sine of pi over 2, which is 1. So I'm going to have negative 4 minus 2 times 1, right? Which is going to give me negative 6. Next, when t is pi over 2, I have 3 pi over 2. Sine of 3 pi over 2 is negative 1. So I'll have negative 4 minus 2 times negative 1. Negative 4 plus 2 is negative 2. Okay? So then we're going to move on to doing our horizontal tangents. Our horizontal tangents have a very similar feature. It's going to be where I take the y derivative and set him equal to 0. So notice here, that's going to give me 15 times the sine of 3t, because the derivative of cosine is negative sine, derivative of 1 is 0, have my chain rule of 15. So just like before, I'm going to be setting the major portion equal to 0. And sine is usually 0 at 0 and pi, right? So 3t either equals 0 or 3t is equal to pi. So t is 0 or t is pi over 3. Now, what is this going to do up here? Sine 3t is 0, which means the negative 4 is going to be constant in both of them. I'm going to have a negative 4 in both of these points. So then the y value is going to fluctuate here, right? If t is 0, cosine of 0 is 1, and I have 1 minus 5 times 1. So then 1 minus 5 is negative 4. Next, when t is pi over 3, I'm getting cosine of pi, right, which is negative 1. Negative 5 times negative 1 is positive 5, plus 1 is going to give me 6. So I've got my two horizontal tangent points. Okay, from what I said earlier, it should make a little bit of sense that there's 4 of these, because if we are noticing the pattern between the sine and the cosine here, right, it's either circular or elliptical, you should have 2 horizontal and 2 verticals, right? Because if it's going to go around, right, you have top and bottom and left and right. Let's go ahead and seal the deal on that idea, convert it into rectangular form so that you can see. I know that sine squared of 3t plus cosine squared of 3t is equal to 1, right? Normal trig identity. Okay, so this means that sine 3t all squared right here. If I solve for sine 3t, notice that that's going to be x plus 4 divided by negative 2, right? Because I would add the 4 and divide by the negative 2 to get my sine 3t. Plus cosine 3t is going to be y minus 1 divided by negative 5 squared, like so. Okay, so then shape this up a little bit. I've got x plus 4 squared over 4 and y minus 1 squared over 25, like so. So this is definitely an ellipse. We can tell because the coefficients here are different. And of course, you could also have insinuated that from up here. Okay. So while we're here, let's go ahead and list out some of the important points from the other ones here. You can tell already that since this thing has been shifted, that its center is going to be negative 4 and 1. Now those numbers should sound familiar, right? The negative 4 was constant here, the 1 was constant here. That should make sense to you. The vertices, remember, are always on the major axis, right? So which one of these two is the major axis? The y, right? Because this one's larger. Okay, so notice my b value here is 5. And notice my a value here is 2. So the length of my major axis is going to be 5 on either side of the center, right? So 5 up and 5 down. The vertices on the major axis are going to both have a negative 4. And then 1 plus 5 is 6, 1 minus 5 is negative 4. Again, those points should be familiar to you because that's these, right? The horizontal tangent points. Again, visualize this. It's an ellipse, right? The top and the bottom should have horizontal tangent line points, okay? And then these other 2 points, the negative 6, 1, the negative 2, 1, notice that if I do negative 4 plus 2 and negative 4 minus 2, I get these exact 2 points. So those are the left and the right extremes of the shape. Now what about the foci, right? The foci we're just going to draw in afterwards, but to compute those, remember we do the c squared equals a squared minus b squared absolute value, right? So a squared is 4 and b squared is 25. So c squared is going to be 21, right? So c is the square root of 21. This is going to be the distance to the foci from the center, right? Since the major axis is on the y-axis, then my foci are going to be negative 4 and 1 plus square root of 21 and negative 4, 1 minus square root of 21. Okay, so now that we have computed the C length and gotten the foci, we have several points to graph. We know what shape we're supposed to be graphing. Let's go ahead and dig in to doing that graph now, right? The center is at negative 4, 1. So right here. Okay, let's go ahead and do the major vertices here. We're going to have negative 4, 6, negative 4, negative 4. Then I've got my other two tangency points over there, the negative 6, 1, and the negative 2, 1. You can see it's starting to come together as an ellipse there, right? So here we go. Let's see how good I can do. Okay. Now, the foci are going to be located at the square root of 21 distance there. So let's see, square root of 21, 4.58 plus 1, 5.58. So really, really close. 5.5, a little bit more than 5.5. So we're talking about right here. And then, of course, naturally it's going to be right here. Those are going to be my foci, those 2 points there. Okay, and also don't forget, when you graph a parametric curve, you always want to throw the orientation on there too. We actually have enough information to do that now, right? Because we know the location of t equals 0, and then we also know the location of several other positive values that come after it, right? T equals 0, we plugged in, and we got the negative 4, negative 4, right? Because it's when the sine was 0, so negative 4. And then when cosine was 0, I got 1 minus 5. So t equals 0 is right here. And then t equals pi over 3. Well, no, let's do t equals pi over 6, right? Because pi over 3 is just the other peak. You don't know which way it rotated. But if you do t equals pi over 6, right? That's even before pi over 3. T equals pi over 6 was the one that gave me the negative 6, 1. Remember, because cosine was 0, so we got the 1. And then pi over 6 gave me pi over 2 here, which was negative 4 minus 2. So this is t equals pi over 6 is at the negative 6, 1. Right here, this guy. T equals pi over 6. So notice the direction here, right? My parametric curve is going in this direction. So therefore it must be flowing in this direction, right? In this direction. And it starts at the bottom. I know that that's not the way we typically do our circular objects. A lot of times we start here and rotate the other way. Well, the difference is I've thrown some negatives in, and then I also swapped. Typically x is related to cosine, not sine. Notice we still get the same shape if we flip-flop the sine and cosine relationships there, but it changes the orientation and, of course, the starting point. Okay? All right, so. Next, a really quick question on just making sure you remember the skills of converting between the three different systems discussed, right? So we've got rectangular, parametric equations, and polar coordinates. All three are valid systems, and we're, just some examples of converting in between the three. So I've got a parametric equation, and it wants us to convert it to rectangular. We've got a polar coordinate equation, converting it to a parametric. And then we also have the rectangular type, and I want to convert it into polar. Okay, so for right here, this to convert to rectangular can sometimes be a little tricky. We did it in the one of the previous questions, right? We got the ellipse by eliminating the parameter through a trig identity. In this case, I'm just going to eliminate the parameter by direct substitution. So right here, I've got that x is equal to e to the t minus 10. This means that x plus 10 is equal to e to the t, which I would then take the logarithm of both sides. So I have the ln of x plus 10 is equal to t. Now, of course, this does limit our ability on the domain of x. Of course, x was never going to have that from here anyway, right? X is going to be limited by the fact that e to the t is always a positive value, right? Never reaches 0 or negative. So the limitation is still here, but you have to be more proactive about it. And then I will substitute this into y equals t squared plus 2. Right, I'll plug this in here. So then y is equal to the ln of x plus 10 squared plus 2. And of course, I would just finish up with maybe putting that in a shorthand that we use, which is to put the squared here on the ln, like so. And then this would be the rectangular form of that parametric equation. Next, I want to convert this into parametric when it's already in polar. Now, also remember that parametric is sort of open-ended. There's an infinite number of different curves that I could pick for this. However, a really, really quick way to convert this is to remember that this is r, and the x value of something is always going to be r times cosine theta, and the y value is going to be r times sine theta. So then a parametric version of this curve, I would say c is equal to where x is going to be -3 secant 2 theta tangent theta cosine theta, and y would be -3 secant 2 theta tangent theta sine theta. And then you could, reduce as necessary here, and then limit your domain or whatever of the theta value as necessary as well. Typically, what we would end up doing is just saying that theta is between 0 and 2 pi, and then a lot of times we won't even include the 2 pi, but I'll just do it here because it's going to have to meet up. Right? So that's really all you have to do for that one. Next, converting this one into polar. Okay? So then for here, I want to convert this into polar by recognizing the same sort of relationships here, that x is r cosine theta and y is r sine theta. So then what I have here, well, okay, before we even do that, let's make it a little bit nicer in rectangular even. This is going to be -3x plus 3. If I add 7, I have y as -3x plus 10. And then y is r sine theta, -3r cosine theta for x, and then plus 10. And remember, the goal in polar is to have r isolated. So I'll pull this guy over and factor the r out. I'm going to have r times sine theta plus 3 cosine theta is equal to 10. All I did was add the 3r cosine theta, and then since they both had r, I factored it out. Now this whole chunk is multiplied times r. I'm going to divide it from the 10. So then my final form is r is equal to 10 over sine theta plus 3 cosine theta. And that's where I would stop for that one. Next, let's throw a little calculus into the polar coordinates. I've got r equals 4 sine 3 theta, and I'm asking that you find the area of one petal and just set up the integral for the length of the curve around one of the petals. Okay, and after we set up the integral, you'll see why it's just a setup problem. Okay, so now computing the area of one petal means that I'm going to be integrating between two, a beginning point and an ending point from A to B, and I have to do 1/2 r squared d theta. That's how we do area in polar coordinates, right? Okay, well, I've got the r squared, there's no problem there, and then d theta will follow naturally, of course, after this. The trick is knowing where to begin and end. So I'll have 16 sine squared 3 theta, d theta here. But I need my boundaries on these things, right? So I'm going to take a look. Remember, we're doing the area of one of these petals here. So all I need to know is r is equal to 0 at the beginning, right? Because it is sine theta. I need to know where after it goes around, because it's going this way, right? It draws this way, and then it comes down through here and goes this way, then back up this way, and this way, then back to the start again. Okay, so it goes around like that. I need to know where does it hit the interior point right there again. So all I'm going to do is I'm just going to let r equal 0 so that I can tell all of the points when this thing should be hitting the center over and over again. Right, so that's 4 sine 3 theta is equal to 0. And therefore I'm really just looking for where the sine 3 theta is equal to 0, right? Okay, so sine 3 theta, sine is 0 at 0 and pi, and then 2 pi and 3 pi and so on. Okay, so let's see. 3 theta would have to equal 0, pi, 2 pi, 3 pi, so on and so on. If I divide everything by 3, you see what I get is 0, pi over 3, 2 pi over 3, pi, so on and so on. Next will be 4 pi over 3, and on and on and on. Okay? But pi in this case is actually far enough that this thing would complete its journey. Whenever you have an odd number of petals like this and it's not rotated or offset like that, then it's going to go through just 0 to pi, and then it's going to meet back up and then start over again. So this is actually the whole breadth of the entire curve here. And what I need to know is just the first petal. So it starts here at 0. And then when theta hits pi over 3, it has gone all the way around this petal and come back to the center again, because that's when r equals 0 again. Therefore, my bounds here are going to be when theta is 0 and theta is pi over 3. And then that's going to carry on for the length of the curve integral as well. Okay, so let's finish this guy up here. I'm going to pull my 16 out. 16 times a half is the 8. And then how do I integrate a sine squared? I have to use the power reduction formula, which is going to pull out a 1/2 again. So I'm going to have 8 over 2. And it's going to be 1 minus the cosine of double the angle. Double 3 theta is 6 theta. D theta. Okay? If you're a little rusty, then let me just write down that for you. The sine squared of some value, I'll use x, since x isn't being used here, is equal to 1/2 1 minus cosine 2x. That's the power reduction formula that I'm using here. Okay, so 8 over 2 is 4, of course. And then I'm integrating, so that's going to give me theta. And then the integral of cosine is sine 6 theta. But then for the chain rule to be accommodated, I have to put 1 over 6 times that. And then this is being evaluated from 0 to pi over 3. Now, when you plug 0 into sine right here, sine of 0 is 0. Also notice that pi over 3 times 6 is 2 pi. Sine of 2 pi is also 0. This whole chunk right here, this guy, is going to zero out in all cases. So all I have left is putting the pi over 3 in here, because notice if I put 0 in, right, I get 0. So this is just 4 times pi over 3, right, or 4 pi over 3 is going to be the area of one petal. Naturally, since there are 3 petals, you could then insinuate the area inside of the entire shape would then be 4 pi. Okay, now let's set up the integral for the length of a curve. Right? Well, the formula for the length in polar coordinates, remember, is the integral from a to b square root of r squared plus dr d theta squared. And then it's in the coordinates of d theta. So it's slightly different than in our rectangular counterparts where it's 1 plus some sort of derivative. Okay? So then I have the integral for one petal we've already established is from 0 to pi over 3. It's going to go around the edge of this curve here. And then I'm going to have the square root of r squared, so that's 16 sine squared 3 theta, plus, now dr d theta, right? I'm going to take the derivative here of this. So dr d theta, the derivative of the sine, right, is our cosine. So I'll have 4 times 3 cosine 3 theta for my derivative there. So naturally, of course, I'm going to have a 12. And then it's squared. So that's 144 cosine squared 3 theta d theta. And that was all that was asked of us to do here. That particular integral being an elliptical integral of one of the major types, and very, very not fun to work through. So if you ever needed to actually get the length of this, of course, you could always plug it into some sort of software, or you can begin the process of using Simpson's rule or one of the other infinite series methods or something to approximate this integral. However, at this point, we were only asked to set it up. So there we are. Now into our vector applications and calculations. So we have 2 vectors that are drawn for us, the r vector and the v vector. And then we're asked to create a third vector, vector a. And then we have a few calculations with the various 3 vectors here. So let's start by reading the vectors here. I see vector r pointing up here, and I want to get the 2 components here. So then all you have to see is that r is right above 5 and right across from 2, and it starts at 0, 0. So then the r vector here would have to be the vector 5, 2. And then you can see the v vector is underneath 7 and across from -4. So then my v vector would be the vector 7, -4. Okay, so now we need to create the a vector. A is 5v plus 3r. So a is going to be
5 times 7 negative 4, right, because that's V, plus 3 times 5, 2. Okay, so A is going to be 35 plus 15 and negative 20 plus 6. The A vector could be represented as the 50, negative 14 pairing like so, but then it asks to write it in basic unit vector form. So then we would say that the A vector is 50i minus 14j. And of course, if you wanted to do in 3 dimensions, you could also add in either a comma 0 on one of these or plus 0k for the 3rd dimension. Okay, now what about the unit vector in the A direction? Let's call that unit vector vector u. We'll be a little original there, right? We'll call it vector u for unit vector. So then this u would be equal to the vector A divided by his own magnitude. And that's how we get a unit vector from an already created vector. So then I'm going to be setting up the A vector, which is 50, negative 14. And I'm going to be dividing it by the square root of 50 squared plus 14 squared. And yeah, I did leave off the negative, but remember that's because when I square, the negative is going to go away anyway. Okay, so then what I get is the vector 50 over the square root of 2,696. That's what it is. 2,696, comma, negative 14 over square root of 2,696. The square root can be simplified. You can take out a 4. 2,696 divided by 4 is 674. So then we finally get the vector 25 over square root 674 and negative 7 over square root 674. Of course, from there, should be pointy right there. From there, you could also get the decimal if you so wish. That particular form is fine for all of the things that I have ever required of my students. Okay, next, calculate the angle between the R and V vectors, right? So in other words, if I label this angle right here, let's label it phi, right? Then remember, the cosine of that angle phi is going to be equal to R dot V divided by the magnitude of R times the magnitude of V. Or another way of putting it, it's like you're dotting the 2 unit vectors in the R and V direction. Okay, so R dot V, we have 5 times 7, 35, right? And 2 times negative 4, minus 8. And both of these lengths are going to be in a square root here. So I'm going to just make it one big square root to make it easier. R is going to be 25 plus 4, because I'm squaring those components, times 49 and 16, like so. Okay, so 27 divided by the square root of 29 times 65. Okay. So then my angle phi, I'm just going to do an inverse cosine of that computation. Right? And what I got was 51.5 degrees. I have also seen the alternate method of finding the angle for each vector. In other words, the vector angle, right? I could find between the x-axis and r and between the x-axis and v. Remember, the vector angle, you can do a tangent of, something like theta r. The angle for vector r would be the ry component divided by the rx component, and you can do the same thing for v, right? If you find the theta angle for each of them and then either add or subtract depending on how your angles are measured up. In this case, the two angles would add, of course, to get the angle in between. You could do that also, okay? However, this is one method where you don't have to problem solve and piece things together. You can just crunch the numbers out. Dot product does make that process a lot better. A quick vector application. Calculate the force required in pounds to hold a 100-pound brick from sliding down a frictionless ramp that's inclined 35 degrees above horizontal. Okay, so I say it's a quick application because we can use the magnitude of a projection to quickly make this computation. Notice that the weight, the 100-pound weight vector, is technically here, right? Pulling down on the object. The projection of this, go a little bit shorter. The projection of this onto the ramp gives us this piece right here being projected, pointing in this direction. In other words, that's the component of the weight that's basically we're fighting against, right? So I just need to balance that. Okay, well, what am I projecting onto? I'm projecting onto the ramp. So therefore, all I need is a vector representing the ramp and then a vector representing the weight. And I can just project one onto the other and find the magnitude of that. Okay, so here we go. The weight vector here is just going to be the 0 and then 100 downward technically, so negative 100 technically. And then the ramp vector here, right, this ramp vector here is just based on the 35-degree angle. The x component would be the cosine of 35 degrees. The y component would be the sine of 35 degrees. And if I'm going to project W onto R, then the force that I'm needed is just the magnitude of that projection. Projection of W onto R. And remember, the magnitude of a projection is just the dot product of the two vectors divided by the length of the thing being projected onto. So in this case, since I'm projecting onto the ramp, it'd be the magnitude of the ramp vector. Fortunately for us, our ramp vector is a unit vector. It's cosine and sine. Cosine squared, sine squared, it's going to equal 1. So really all I have to do is W dot R. So that's 0 times cosine, right, which is 0, plus the negative 100. I'm going to use positive 100 though, because remember what I need is just the magnitude, right? So technically this is an absolute value. 0 plus anything, I'm going to do the absolute value here.
sine of 35 degrees. So once you do that computation, you see that it is 57.4 pounds. Okay. Now some common vector calculations that come up. So I have two vectors that are given to me, L and D. They're in 3 dimensions, not 2. I want to do the projection of D onto L, called vector P. And I want to do the cross product of L and D, L cross D, which I'm going to call vector C, right? Applications of projection come down to, well, like the one we did a moment ago, when you have to do with things like work or force of motion, things like that, where you have one component of a vector affecting the direction of another. Cross product applications can stem all the way back to torque. You need to be able to do a cross product in order to get a torque vector. The only way you get around that is if you only needed the torque magnitude. And then, of course, volume of the parallelepiped formed by L, D, and C, which we're going to be using the triple scalar product, which will be C dot L cross D. And we'll talk about a couple of variants of that. So, projection of D onto L is what this says, right? So then I need to write down my formula for that one so that you can see what I'm doing here. That's going to be D dot L over L dot L, or you could do magnitude of L squared, or whatever way you want to talk about that, and then times the L vector, right? So then to perform this right here, I have D dot L which is going to be 0, right? Because -6 times 0, 4 times -3 is -12, and 1 times 2 is 2. L dot L is going to be 36 plus 16 plus 1. And it's times the L vector, -6 for 1, like so. Okay? So then what I end up with is -10 over 53 times this vector. Finally, I can just go ahead and write it out. That gives me 60 53rds, -40 53rds, and naturally -10 53rds. This would be the P vector, the projection of 1. Now, whenever I give this test, I always ask as well with this to describe, because it does take quite a while and a bit of skill to be able to graph it in 3 dimensions. So just describe in words. It just means that I have the two vectors L and D, right? Like so, let's just say it's something like this, and I'm projecting one of them onto the other such that the component of it is in the direction of the one being projected on. So you would describe that in words. This is the component of D. This is the portion of D vector that affects the L direction, or has an effect in the L direction. That's how you would describe that in words. Okay, next, the cross product of L and D. Okay, let me divide this up here. So then the C vector would be equal to the determinant I, J, and K, like so. And then the L vector is -6, 4, and 1. And the D vector is the 0, -3, and 2. Right? Okay. So then from here, the way I do my determinants is I rewrite those first two columns, right? I would rewrite my I and J columns here. The -6, the 4, the 0, the -3. I know some of you physics people out there are cringing. This is an easy way for us to not have to memorize formulas. So then I'll be doing my diagonal multiplications here. So I'll have this one, and this one, right? So I'll have my I direction, my J direction, and my K direction pieces. I have 8 in the I direction, 0 in the J, and 18 in the K. Then the other three, I'll have 0, so -0, because this is, don't forget the lower ones are the negatives. Then negative 3 times 1, so +3 in the I direction, and again -2 times -6, so +12 in the J direction. So therefore my C vector here is the vector 11, 12, 18. Okay, and if you're asked to describe this one, right, don't forget that when you're describing a cross product vector, if you have the vectors L and D, like what I do here, then C is going to be the vector that, according to the right-hand rule, so let's see, what did I do? D onto L, so this is D right here, and this is L. If it's L cross D, right, then L crosses into D with my right hand, means that the C vector would be coming out of the board here. The cross product is the vector that is perpendicular to both of those and in the direction according to the right-handed curl between them, right? So you would just describe that in words. This is the vector that is perpendicular to both L and D. You could check that with dot products, by the way, right? If I want to prove that this is perpendicular to one of the other ones, I could just dot it. For example, if I dot it with D, I get 0, -36, +36. So it zeroes out, right? Same thing up here, right? -66 +48 +18 is equal to 0. So this is the vector that is perpendicular, orthogonal to both of these other two vectors. And then lastly, the volume of the parallelepiped formed by L, D, and C. So then this can be thought of a couple of different ways, because remember we just said that L cross D is equal to C. So you could take a shortcut here and say that this is C dot C, or in other words, the magnitude of C squared, right? We could do that. That would actually be the shortest way to perform this thing. So I would just square 11, 12, and 18 and add them together, right? And that should be what we should get. However, what I am going to do instead is the way that the triple scalar product is typically performed, okay? We'll just call it V for volume here. So V is going to be equal to, the triple scalar product is set up very similar to cross product. I have the -6, 4, and 1. I have the 0, -3, and 2. But instead of I, J, and K, I put the components of the other vector, so 11, 12, 18, like so. And basically what's happening is the parallelepiped is just the other two vectors with the third vector on top of it, and it's you translate it for the top and the bottom, and you make sort of the three-dimensional diamond-ish kind of shape, right? And we're doing the volume of that. Of course, from here, what I have is just another determinant, so I'll be performing it the same way. I'm going to take those first two columns and rewrite them, right? 11, 12, -6, 4, 0, and -3. Except there's no vector part of it this time. It's just the multiplication here, right? So I have 11 times 8, 0, and then 18 times 18. I'll just do this quick. It's 18 squared minus 0 minus negative 33, and then right here minus, which is going to end up being plus, in this case 12 squared, so 144. Came out really nice. All right, just to save time here, 88 plus 18 squared plus 33 plus 144. 589. Okay, so keep in mind the way that a triple scalar product is typically performed is by doing this type of determinant while putting the three vectors in the order that you see them in, and of course there's other ways of rearranging it. We did have the other shortcut this time. We would actually end up at the same result if you did 11 squared plus 12 squared plus 18 squared. Look, there's the 18 squared, the 12 squared, and then the 11 squared is here. So that there was, in this case, and it's just because of the way the vectors are arranged that C was related to them. Okay, a triple scalar product doesn't always have to be that way. So definitely learn the skill of doing a triple scalar product this way, and that the triple scalar product is related to that particular type of volume, among other calculations with 3D vectors as well. So now let's finish up with a torque problem. Some more vector applications. I've got a pedal mechanism here. The length from the crank all the way to the pedal is 11 inches. And I've got someone that's weighing 125 pounds pushing down with, just all their weight on that one pedal. Maybe they're pumping up a hill and they're just grinding their whole weight on it, whatever. Okay? At the moment that they're putting the force down on the pedal, the crank of the pedal is at a 23-degree angle from the horizontal ground, right? So in other words, if you could have the ground right next to it, right, so to speak. So what kind of torque is being generated at the crank right here is what we're talking about. Okay, so don't forget that torque is R cross L, or R cross F, if you will, whatever. Okay, so right here, if we just want the magnitude of this, right, regardless of finding this, if we have the right kind of information, we can easily compute the magnitude of a cross product by just doing the magnitudes of the constituent vectors times the sine of the angle in between them. I'll call it theta RF. Well, fortunately for us, we've already got that information for the most part. Now, we do have to remember that the common American unit for work or energy type related things is the foot pound, right? So we should say this right here is in foot pounds. Well, our force is already measured in pounds, good, but is our distance of our radial vector in feet? No, it is not. It's in inches. Okay, so we're going to need to convert that. The magnitude of the R vector here is going to be 11/12 feet, right? 11 inches divided by 12 inches is how many feet it would be. The magnitude of the force being 125 pounds. And then the sine of, be careful, this 23 degrees right here is not the angle between the vectors. if you transfer the force vector, right, down some, and then notice that the r vector is here, then the setup that we have is like this. Here's the r vector, right? Here's the f vector. So the angle in between them, theta RF, is right here. Whereas we have this angle with the horizontal. Well, if you look at the way the force is being applied straight down, that means that this is going to be a right triangle here. That's fortunate for us. We're forcing using the weight in the direction that it's intended. Okay? So then this theta RF right here is just going to be the complement of 23 degrees. Or in other words, 67 degrees. So then we crunch that, right? Put all of that together. 11/12 times 125 times the sine of 67. And I have 105.5 foot-pounds. Now, what if you had to do the cross product, right? You would actually have to create these vectors and do the cross product to find the torque. So this is actually the better way to do the problem, but incidentally, you could actually create the r and f vectors. R would have to be the vector with 11/12 times the cosine of 23 degrees and the sine of 23 degrees and 0. And then the f vector would be 0 in the x, right? Negative 125 in the y, and 0 in the z direction. Okay? But I want you to notice this. I'm supposed to do r cross f here, right? R cross f. So you need to realize that for this to work out the way that we want it to work out, right? R and F are in the same plane, right? They're in the plane of the motion of the petals. So I could actually go through the whole rigmarole like we did in a previous problem where you set up the cross product as that determinant with the IJK. Sure, you could go through all of that, right? And it would work out just fine. But if I really wanted to do this cross product, use the old noggin a little bit, I could just realize that R cross into F is just going to be this vector coming out of the board in the Z direction. Notice they have no Z component. So the cross product is going to be purely Z component. It's going to zero out everything else. And what are you going to be left with? This, right? So your torque vector is going to be equal to 0 and 0, and the 105.5 purely in the K direction. Okay? And then the direction is, I'm doing R cross F, right? So I'm actually doing, oh, well, actually, you know what? It should be negative. It should be negative because the way R is pointing right here, right? If I transmute it here, R into F, my right hand points into the board like that. Regardless, you can see the way that the torque vector is being displayed. And the important part is because I see that these are planar in the XY plane, then the torque vector is going to be purely Z component like that. That's knowing your cross products, knowing how your torque is working with a cross product. And then this is the actual answer to the question, just the magnitude of it. Okay. So I hope all of these problems are helping you in studying for this third installment, this third big unit in Calculus 2. Remember, don't focus on memorizing individual problems. Pick them apart. Find the skills. Practice those particular methods. And make sure that you can problem solve a little bit to get these things to work for you.